Alright, let's talk about the buffer solutions. One thing about buffers that I mentioned earlier is that they do resist changes, drastic changes in pH. And generally speaking, there's a way of calculating how good a buffer is at resisting these pH changes. And the reference value is to see, what kind of concentrations you would need to add of a strong acid or strong base to make a change of plus or minus 1 pH units to the solution containing the buffer. So for instance, let's say we have acetic acid and acetate making up your buffer. We want to find out, what kind of concentrations we will need to have in order to make changes of plus or minus pH units. So look at the Henderson-Hasselbalch equation for your buffer. One thing you could do is subtract the pKa from the pH. So you could have an initial pH value that you are referencing. Subtracting the pKa from it will give you the log of the ratio of base over acid. And then basically this change in pH right here, we can equate to the log of the base over the acid. Now, I'm going to go under the assumption that the change equals 1. And this is a very simplistic way of looking at it, right? Because it doesn't necessarily mean that the pH minus pK is always going to be plus or minus 1. But I'm oversimplifying the idea a little bit so that you can see where I'm going with it. So if the change in pH is plus 1 or negative 1, we're going to have some specific features happening. Take the antilog, meaning raise 10 to the first power or raise 10 to the negative 1 power, and you'll end up with the following two expressions. 10 equals the ratio, or 0.1 equals the ratio, which in essence means that 10 times the concentration of acid are equal to the concentration of base in one instance, or in the other one, a tenth of the concentration of the acid equals the concentration of base. Alright, so let's see what happens. Okay, so in the best case scenario, the best buffer that you could actually prepare for any type of solution is one where the concentrations of the acid and the conjugate base are equal to each other, because this gives you the maximum amount of change that can happen on either direction without favoring one versus the other. So I'm going to go under this assumption that the initial concentrations were equal to begin with. Alright, so then what ends up happening is that the initial concentrations of HA and A minus, as you add strong acid or strong base, are going to be changing. But altogether, since A has to remain constant, right, the concentration of A itself has to remain constant, the summation of HA plus A minus has to be equal on either side of the equation, whether it's the initial amount or the final amount. Alright, so if we utilize the equation here, meaning that the initial concentration of HA is equal to the initial concentration of A minus, then HA initial plus A minus initial has to equal 2 times the initial concentration of HA. Alright, and that applies to either version of the equation here. Now the difference is that we also have an expression for the final concentrations. On the one hand, 10 times the value of HA is the value of A minus. On the other hand, 1/10 of HA is the value of A minus. So we're going to literally substitute those expressions for the value of A minus. Okay, so we have the following on one end of the spectrum, and then we have the other expression right here for the other opposite extent of reaction. So we have 2 times HA initial equals 11 HA final, or 2 times HA initial equals 1.1 times HA final, which means that the value of HA final is equal to 2 over 11 or 2 over 1.1. And what this tells us is that the final acid concentration is going to be 0.182, the value of the initial HA concentration, or it's going to be 10 times more than that. Alright, so we're almost at the point where I'm about to provide you with a proper equation. Alright, so if this is the value of the final concentration in terms of the initial concentration, then all we have to see is the change. What is the change in concentration from the initial value to the final value? Okay, and so we're going to literally substitute the 0.182 HA or the 1.82 HA into the value of the final concentrations, so that we get an expression for the buffer capacity, which is given by the symbol beta, in terms of the initial acid concentration. And what you find out is that whether you're raising the pH or decreasing the pH by 1 unit, so long as you have the initial amounts of HA and A minus at the very beginning of the solution or the problem, all you have to do is multiply that initial concentration by 0.818, positive or negative, to find out the buffer capacity. And needless to say, as you do increase the concentration, the initial concentration of the buffer, you increase the buffer capacity. And another way to think of this is that the higher the concentration of your initial conjugate acid and conjugate base are, the more HCl or the more sodium hydroxide you're going to need to add to that solution to make drastic changes into the pH. So that's what the buffer capacity is telling you. So just to give you an example, if you start with a solution for which the concentrations of the conjugate acid and base are 1.5 times 10 to negative 2, then you can find out the buffer capacity simply by multiplying the concentration, the initial concentration of the acid by 0.818, and you'll find out that the buffer capacity is 0.0123 molar. Okay, and it's as simple as that. The derivation was a little bit long, granted, but as you can see, the actual calculation is simplistic. But the one thing I want you to realize is that this applies if and only if the concentration of the conjugate acid and the conjugate base are equal to each other from the get-go. Alright, now let's do pH calculations involving buffers. Alright, so the idea is that the conjugate acid or the conjugate base are going to be potentially ionic, right? In this case, the conjugate acid is neutral, but the conjugate base is definitely ionic, right? What you want to keep in mind is that anything that's ionic has to have a counter ion to balance its charge. So if you are to prepare a solution that contains a buffer, let's say in this case acetic acid with acetate, you're going to have to use acetate in the form of a salt. That could be lithium acetate, it could be sodium acetate, potassium acetate. It doesn't really matter what the identity of the cation is as long as the charge is being neutralized. These are the things that you actually get to use and buy and store when dealing with compounds, right? So you have to consider, in most of the cases, not all, but in most of the cases, you have to consider the salt for the conjugate base in addition to the conjugate acid. So to give you an idea of the type of problem that I could ask you that relates to this, I could say that you have 50 mL of 0.15 molar concentration of acetic acid, which you're adding to 50 mL of a 1.23 molar sodium acetate solution, right? And yeah, so this thing right here, the 1.5 times 10 to negative 2, don't disregard that. That doesn't make sense. So basically what you have to do here is account for the fact that 50 mL of acetic acid are being mixed with 50 mL of sodium acetate. So you are in essence changing the volume of the solutions. In essence, you are diluting them. So we're going to use M1V1 equals M2V2 to find out the final concentrations before we actually apply the Henderson-Hasselbalch equation. So for acetic acid, the initial concentration is 0.150 molar. The initial volume is 50. The final volume, once you combine them, will be 100 mL, meaning that your concentration is 0.075. For sodium acetate, same idea. The initial concentration is 1.23 molar. Initial volume is 50 mL and the final volume is 100 mL, meaning that at the end you end up with a concentration of 0.615. Once you have accounted for the dilution that's taking place upon mixing these two solutions together, now you can apply the Henderson-Hasselbalch equation. And the pK of acetic acid is 4.75. That's given here on the problem. So we're going to add to that the log of the base over the acid. And the base right now is the sodium acetate. So that will be the 0.615. The acid is the 0.075, acetic acid. So we have them in that particular order. We take the we take the log of that and add it to 4.75 to find out that the pH is 5.66. Alright. The last thing that I'm going to mention is how to prepare buffers. When you are in a laboratory, chemistry laboratory, or even a bio laboratory, a biochem laboratory, you are often tasked with preparing solutions that will have a very specific pH. So you know what the pH ought to be, What you don't know is how much of the substances you need to add to make that particular pH. So we're going to do some calculations to figure out what amounts will make the most sense in order to create a solution that has a very specific pH. In this case, I'm going to stick to acetic acid and acetate for my buffer. I want the pH to be 5.40. And what this means is that since we're making a buffer, we can use the Henderson-Hasselbalch equation. The pKa of acetic acid is 4.75. So we can input that in addition to the pH. If you subtract 4.75 from the value of the pH, you will isolate the logarithm of base over acid. Take the anti-log, so raise 10 to the 0.65, that will give you 4.467. And finally, if you multiply both sides by HA, now you have an expression that correlates the concentration of the conjugate base to the concentration of the conjugate acid. Now here's where extra information needs to be provided for you to make sense of what you're going to do. You need to prepare 1 liter worth of this solution so that the pH is 5.4. One thing to keep in mind is that the moles of the substance in essence is what you're after, right? You know that this will have to be 1 liter in volume, so that will be the volume associated with the concentration of the substance. Meaning that you can just look at the, in this case, you can look directly at the moles, okay? So 4.467 times the moles of HA equals the moles of A minus. All right, now here you don't actually know exactly what's going to work out, so you're going to have to guess some numbers, and I would recommend that you stick to simple numbers like 1 or 0.1 or even 10. All right, so if you select 0.1, what's going to for HA, what's going to happen is that you will automatically make the moles of A minus 0.447. And now, if you were to pick 1 for HA, then you will end up with a concentration ultimately of 4.47, which is already kind of high. So you want to kind of keep those concentrations, you know, between 0.1 and I would say 10 at most. But you know, the closer you get to 10, the more drastic and difficult it's going to be to prepare those solutions. But in essence, going with 0.1 as number of moles will yield a concentration of 0.1 for the acid and 0.447 for the base. And this is one of the ways in which you go finding out concentrations. I recommend that you stick to simple numbers, 1, 0.1, and 10. You know, don't go with the intermediates, you know, like 7, or don't make it worse on yourself. You know, don't select say 7.61 for the value of the acid, right? Just make it easier on yourself. 0.1, 1, 10, and then see what happens to the value of the base upon applying that change. All right, so this is it in terms of buffers. We're gonna use this information to move on to the next topic, which is titrations. But make sure to kind of take a look at the buffer preparation problems. I made it look like it was a lot simpler than it is. This actually takes a little bit more thinking than you might appreciate as of now. So I'm just kind of warning you, the buffer prep problems are a little bit more convoluted than I'm making it look, but the procedure is still the same. It's just a matter of you guys getting familiar with the procedure. Okay, with that being said, I'll stop the video right here and I'll see you in the next lecture series.